Hi everyone, welcome to this supplementary video. So in this video, I mainly want to discuss this homework problem that you did in your homework 3, problem 2. I'm not going to solve this problem, but this was a very interesting question that came up in one of the office hours. And I just wanted to clarify some of the aspects of this sort of system. So the basic idea behind these problems is that you have a Bernoulli's equation plus a manometer, right? So we're mixing two concepts essentially. One is hydrostatics, and then one is Bernoulli's equation. So in this problem, it's sort of easy to see and very easy to understand that we'll have P1 rho V1 square by 2 is equal to P2 plus rho V2 square by 2. There is no height because the height is the same in both the systems. And we also know that because areas are given is that A1 V1 is equal to A2 V2. So essentially, if I want to calculate, and I know the velocity one is now higher, so I can essentially say that P2 minus P1 is equal to rho V1 square by 2, and then for the V2 I will substitute in terms of A1. I will say this is A1. So I'm trying to calculate for V2. So V2 is A1 V1 by A2 square V1 squared by 2, or essentially rho into rho V1 square by 2 into 1 minus A1 by A2 whole square. Okay, so P2 minus P1. Okay. So this is the simplest mathematical manipulation using Bernoulli's and continuity together. And we know that A1 is smaller, right? It's a thinner pipe initially. A2 is larger. So P2 is greater than P1. We know P2 is greater than P1. And this is also physical. So what's happening is the kinetic energy, because of the continuity equation, is larger at point 1. There is no gravitational change because it's at the same height. So the pressure is higher at point 2, right? And that, which makes sense because the kinetic energy is lower and that energy has to be compensated. So the pressure energy is higher at point 2. Now there are two ways to approach this. The simpler way, and I saw some students stated, and I think that's completely fine. You're very welcome to do this. So let's call this as density of the fluid, which is, let's say, a manometer, right? And then this density is rho, right? So at point 2, we have higher pressure. So the weight on the right part should be higher. Okay. So the other way to think about this manometer part is that the weight should be higher because pressure is higher on the right hand side. And so note that this portion, so this portion that I'm now, this part and this part essentially is essentially the same on both sides, right? And so this the column is the same, the heights, and the fluid is the same in the shaded region. So really, whatever really is happening in sort of this capital H portion. The small h really, as you can see, does not really matter because small h is the same, it's supporting the same weight. So essentially, we can think of this as delta P, or P2 minus P1 is equal to, and the difference in the weight, it is not the weight in either column, it's a difference in the weight, is essentially rho minus rho manometer, and it might be some other thing in the homework problem, times h times g, or gamma minus gamma manometer times h, right? So I'm just used the density. You can also use the gamma specific weight. So that's it. And then you can equate this to the right hand side and you can solve, and this is what you all did in the homework. So this is a shortcut approach. In the sense, you can just physically motivate the weight on the right hand side, right part should be higher. And then, however, the other approach really is, and which is what I want to kind of also discuss, which came up. So this is an approach, and I want to show you from an alternative approach how you can get to the same point, is that you can say, well, I have a point 3, then I have this point 2, right? I have a point 4, then I have point 5, and then I have point 1. Okay, so you can also make the case that P3 plus rho, and I'm using the rho GH rather than the gamma just because of the to be consistent. Okay, this height is rho into H plus H, and I can use hydrostatics. This is the alternative, right? P3 plus rho GH is equal to H plus H is equal to rho 2. Then on the other side, P4 plus rho manometer H is equal to P5, and then P5, which is this step, which I'm now sketching with the arrow 4 to 5, and then I'm going from 5 to 1, and then I can say P5 plus rho normal rho into H is equal to P1, right? You can say this, and then you can essentially sum these two, sum to say P4 plus rho manometer into H plus rho H is equal to P1. Okay, sum them. So P5 on the right hand side gets cancelled out. And then this one I'm just copying again here. And P3 plus rho G H plus small h is equal to P2. Now subtract them. And what you'll get is P3 minus P4. And then you will have rho G H plus H minus rho manometer. By the way, there is a G I forgot. Sorry about that. There is G I forgot everywhere, so do correct that. Apologies for that. Manometer Hg plus rho Hg is equal to P2 minus P1. And this will become easier. So this gets cancelled. Sorry, not this one part. This gets cancelled out. And what you will get is, and P3, because we are in the manometer fluid, P3 is equal to P4. Okay, P3 is equal to P4. So this gets cancelled out, and what you get is rho G, or rather rho minus rho manometer into Hg. Hg is equal to P2 minus P1. So this answer is identical to the one that we just simply wrote by this sort of idea of difference of weight. Okay, this is a more formal derivation. So let me first recap. First idea is, you can say the difference is simply the difference of the weight being supported at those 2 points, and that weight being supported by 2 points comes out to be this. Okay, or you can do the full derivation, and you can sort of say this is the other derivation. Okay, now first note that rho manometer has to be lower than rho. In this case, this fluid has to be lighter, and this is 400 kilogram per meter cube instead of 1000 kilogram per meter cube for water. So that's why it works out. So if it was a heavier fluid, then you would need to have this rho manometer on the right hand side, because the right hand side needs to support more weight. In this case, it was filling the left hand side more because it was lighter fluid. So if it was a heavier fluid, we'll have to kind of have the rho manometer will have to be higher than rho to have sort of like the balance. But more importantly, there was a very nice question. One of the students asked it, well, the question was, why can't I go and I'll create this another point 6? So and her question was, well, you can say P3 is equal to P4, but can't I also say P5 is equal to P6? I'm also still going into the same fluid. And if you use, try to do this, if you say P5 is equal to P6, you get a wrong answer. Okay, you get a wrong answer and you don't get the right answer. And why is that? So that happens because note, when you're going from P5 to P6, you're moving horizontally in the flowing fluid. So you cannot move horizontally. You cannot go from 5 to 6, because you're moving horizontally in the flowing fluid. In the flowing fluid, and the flow is happening horizontally as well. So remember, in the Bernoullis, if the fluid, we cannot have sort of this idea that this pressure will not change horizontally in the flowing fluid. Pressure can change horizontally, but then why am I allowed to do the P3 equal to P4? P3 is equal to P4 because I'm doing this in the non-flowing fluid, and that is the manometer fluid. That's why I'm allowed to go from 3 to 4. But I cannot say P5 is equal to P6 because you're going horizontally in the flowing fluid. This is a very subtle point and very good one, which was raised, and I thought it would be useful. So to recap, essentially, when you're trying to get manometer problems with Bernoulli's equation, I would advise that you need to really understand this. So you can try this alternative derivations yourself to convince yourself that you will always get the same answer. Simplest approach is to think about wherever the kinetic, if the potential energy is the same, for instance, in this horizontal pipe, the potential energy is the same, then the higher kinetic energy will have the lower pressure, or the lower kinetic energy will have the higher pressure. And so whenever you have the higher pressure, it needs to support more weight. So in this case, where there is a lower kinetic energy, which is 0.2, it has to support more weight. So the right hand side will need to have more weight in the left hand side. And then the difference between the weight is simply this one capital H column. And so you can use that to find the pressure difference. That's point number one. Alternatively, if that's a little confusing to you, you can essentially go from point to point, much like the manometer problems we used to do. However, you cannot move horizontally in a flowing fluid. If the fluid flow is happening horizontally, you cannot move in the flowing fluid. However, you can move horizontally in the non-flowing fluid. So this is the P3 minus P4. I am allowed to say that because that line 3 into 4 is actually in the it passes in the stationary fluid. So that's where I could do the hydrostatics part. Okay, so that is what I wanted to cover in this video, and then I look forward to seeing you in the next video. Thank you.